Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Today we're going to talk about calorimetry and heat capacity or specific heat capacity. So we mentioned heat in our previous lecture is just a form to transfer energy. And how to calculate heat, besides just giving you a number from a question, experimentally how to calculate this heat and also heat capacity. That's something we're going to talk about in this video. So specific heat capacity or heat capacity is a property of a material. Specific heat capacity can be expressed as a lowercase c. It means the quantity of heat required to change the temperature of 1 gram of a substance or material by 1 Kelvin. Okay, for the specific heat capacity, it's like density. It's an intrinsic property of a material, which means different materials will have different specific heat capacity. It should be in the unit of joule per gram per Kelvin. Well, it can have other units, but this one is a SI unit. And it's a common SI unit. Okay, if it's a derived SI unit, it should be joule per kilogram per Kelvin, right? So for the equation, we can use Q equals to Cm delta T to calculate the heat released or absorbed by a material from a surrounding or two surroundings. So C is the specific heat capacity of the material, M is the mass of the material, delta T is the temperature change of the material using the final minus the initial. In the textbook, it gives table 6.2 where you can find many values of heat capacities of common materials. If you look at this table, which one has the largest heat capacity, specific heat capacity? Well, you can find it's the water. Okay, water has a relatively large specific heat capacity, and that means given the same amount of heat, the temperature change of water will be small. Look at this equation. If the heat is the same, the larger heat capacity, the same amount of water, same mass, the smaller change of temperature will be. So because of that, water is used in, many circumstances as a buffer to slow down the temperature change of other materials. A concept similar to the specific heat capacity is just, the heat capacity. It's an uppercase C. Okay, so heat capacity is the quantity of heat required to change the temperature of a substance or material by 1 Kelvin. Compare these two definitions. We don't define the mass, in the heat capacity because that's already included here. For example, the specific heat capacity of water is 4.184 joule per gram per Kelvin. Then if we have 10 grams of water or 100 grams of water, the heat capacity will be different, but the specific heat capacity are the same, right? So for 10 grams of water, the heat capacity is a specific heat capacity times the mass. Then for 10 grams of water, the heat capacity is 41.82. Then 100 grams of water, the heat capacity is 418.4 joule per Kelvin, right? So please make sure you know the differences between the two concepts. And the heat capacity, as I said, is related to the amount of a material. If you have more material, you have larger heat capacity. The unit is in the joule per Kelvin. And for the equation to calculate the heat is the heat capacity times the change of temperature. Okay. For the equations in red, you need to be able to master, understand, and know how to use them in a problem. Similar to specific heat capacity, there is another concept called molar heat capacity. It's C lowercase m, okay, C sub m. Like the specific heat capacity, the molar heat capacity is normalized to 1 gram of a substance or material. So you can see the unit is changed and the equation used to calculate the heat is slightly changed. All right, so for the specific heat capacity and heat capacity, we can use experimental tools to calculate that. Now I'm going to introduce you two different devices to calculate the specific heat capacity or just the heat capacity. So first one is the constant pressure calorimetry. Calorimetry means the method to calculate heat. For processes that take place at a constant pressure, the heat transferred Q sub P is often measured in a coffee cup calorimeter. Calorimeter means the device to calculate heat. Okay, so here is a schematic of what a coffee cup calorimeter looks like. We have two layers of coffee cup. Try to eliminate the heat transfer from inside to the surroundings. Okay, in this coffee cup, we have a certain amount of water, and it's a known amount of water. We know the mass of that. Also, we have a plug. Through the plug, we have a stirrer that stirs the water to make sure every part of the water shares the same temperature. We also have a thermometer that going through the cap and immerse into the water to record the temperature of water. So for that, we know a sample. We have a sample. We can weight the sample beforehand, and we should know the temperature of the sample beforehand. That's the initial temperature of the sample. Then we drop the sample into this coffee cup calorimeter, seal the plug, stir the water to see what happens in the temperature of water. As you imagine, if the sample is hotter than water, sample will cool down, water will warm up. If the sample is cooler than water, sample will get warmer, water will cool down, right? But no matter which way, you can tell the difference from the thermometer. In the very end, these two will reach an equilibrium, which means the water and sample will have the same temperature, share the same temperature, and that can be read from the thermometer. In this case, we think if we define the sample as a system, the water as surroundings, we can say the heat released from sample or absorbed from the sample equals to heat absorbed by the water or released from the water. Remember, we define Q as positive and negative based on different definitions here. So in order to make the two values equal, we need to put the negative in the Q from the sample. So negative Q sample equals to Q water. Okay, we are kind of comparing two definitions of the system. When we say Q sample, we define the sample as a system. When we say Q water, we define the water as a system. So that's why we need to put the negative here. Then plug in the number. For sample, we have Cm delta T sample. For water, we have Cm delta T water, right? So if the sample is hotter than water initially, then just take an example. The sample delta T sample is smaller than 0. Well, the water delta T of water is larger than 0. Then we can just configure this equation. Then we can get the specific heat capacity of sample equals to the Cm delta T of water, the total heat of water, divides the mass of sample, divides the negative delta T of sample. Or if we want to calculate the heat capacity, we can multiply the mass of sample on both sides, and on the left we have the heat capacity of sample that equals to the Cm delta T of water divides the negative change of sample temperature. Okay, so you can see the coffee cup calorimeter is a relatively simple design, and sometimes it has errors. As you can see, only the two layer of the coffee cup may not 100% prevent heat transfer from water to the air, to the big surroundings. So there is a more accurate device to calculate the specific heat capacity or heat capacity. That's called or we use that as the constant volume calorimetry. And that is carried out in a bomb calorimeter. Okay, here is the schematic of bomb calorimeter, and it's usually used to measure the heat capacity of a combustible material. That means the material that can burn in oxygen. Okay, so there are different layers of the cage of this calorimeter. so which guarantee a very good isolation, thermal isolation from inside to outside. So in the very center of this device, it has a reactor filling with oxygen. So in the reactor, there's also a coil that can use to ignite the sample. The surrounding is water-filled container, okay, and still we have a stirrer, we have a thermometer to read the temperature of the water, and also, you know, make sure the water has the same temperature everywhere. When we use that, we need to have a sample that still needs to be pre-weighted. We need to know the mass of the sample beforehand, and also we need to know the temperature of the sample beforehand. After we put the sample into this container, then we can dose oxygen in and then use a coil to ignite the sample. It's burning. And then after a while, it burns out, the thermometer can read the final temperature of both sample and the water. So in this case, the heat capacity of the entire calorimeter is known, not, you know, like the coffee cup one. We only know the specific heat capacity of water. We need to weigh the mass of the water. In this case, the bomb calorimeter, the heat capacity of the entire calorimeter is known. So that simplifies our equation. Still here, negative the heat transfer from sample equals to the heat of calorimeter. Plug in numbers. For sample equals to Cm delta T. We need to put the negative beforehand. For calorimeter is C calorimeter, the heat capacity of calorimeter times the delta T of calorimeter. Okay, then rearrange this equation. We can get the specific heat capacity of sample. Use C calorimeter times the delta T calorimeter, divides the mass of sample, divides the negative temperature change of sample. Or, you know, like before, we can calculate the heat capacity of sample. That goes like this equation. The heat capacity of calorimeter times the temperature change of calorimeter divides the negative temperature change of sample. Okay, so these are the two devices. Let's take a look at the heat capacity problem. A 33.2 gram titanium bicycle part is added to 75.0 gram of water in a coffee cup calorimeter at 50.00 degrees Celsius. And the temperature drops to 49.30 degrees Celsius. What was the initial temperature in degrees Celsius of the metal part? It gives you the specific heat capacity of titanium is 0.228 joule per gram per Kelvin. And you can find the specific heat capacity of water is 4.184 joule per gram per Kelvin. Okay, for this coffee cup calorimeter or bomb calorimeter, you can see in our previous two slides the equation we used are the same. That is, the heat transfer from the sample equals to the heat transfer to the calorimeter, right? So in this case, you need to define which one is a sample, which one is a calorimeter. In this case, obviously, titanium is a sample, like the water is the part of the calorimeter. And also, there is a hidden information you should get. That is, from this one is that water in the coffee cup drops to 49.3 degrees Celsius. That temperature, 49.3 degrees Celsius, is a final temperature that is also shared by the titanium part, the sample. So although it does not tell you, but you should know the final temperature of the titanium part is also 49.3 degrees Celsius. Okay, so with that, we can write our equation. And also, since it mentions the specific heat of capacity, we use the Cm delta T equation, right? So negative Cm delta T of sample equals the Cm delta T of water. You just need to remember to put the negative sign here, it does not matter which part you put that in. Okay, so for a sample, specific heat capacity of sample and water, we already know, right? And they have the same unit, can be canceled out, so we don't need to do any unit conversion change. For the mass of sample and mass of water, we also know it from the question, so that's also good. For the temperature change of sample, we know the final temperature which is 49.3 degrees Celsius, but we don't know the initial, and that's what is asked from the equation. Okay, well, from the question. So we can assume that as x and then solve the equation to get x. For the water, the temperature change, we know the initial and final, so we can also get that part. All right, let's try it out. Assume the initial temperature of the sample is x degrees Celsius. So write it out, the temperature change for sample. Please remember the delta T also always use the final minus the initial, okay? So the delta T of sample is 49.3 minus x, final minus initial. The delta T of water is final minus initial again, 49.3 minus 50, that equals to negative 0.7 degrees Celsius. So the negative means the temperature dropped, okay? So for all of these calorimetry problems, the sign can be, is something that was worth you to paying attention to. So don't mess up with the signs. Remember, delta T is always final minus the initial, and that's it. Okay, so plug in the numbers. We have negative 0.228 times 33.2 times 49.3 minus x as a group, and then equals to 4.184, the specific heat capacity of water, 75 grams of which is the mass of water. The temperature change of water is negative 0.7 degrees Celsius. All the values, all the units can cancel out from left to right, so that's great. We don't need to do any unit conversion. So as long as the units are the same before and on the left and the right of this equation, we are good. With only one exception, the temperature has to be in Kelvin or degrees Celsius. If it's in Fahrenheit, you need to do the conversion still. Okay, so now we can solve this equation and get the value of x as 20.3. That's the 20.3 degrees Celsius as the initial temperature of the metal part. All right, this is end of this video, and I'll see you next time.